Okay, this is Dr. Williamson working on a basic solution, base alkaline solution, base solution. But we want to calculate the pH. And this says, what is the pH of a 0.5 molar dimethylamine solution? And the formula for dimethylamine is CH3NH, and I put the aqueous on there. So I wrote the equation of the base reacting with water. We got NH3 plus water makes this plus that. And what's going on, just to teach you guys, is let's do this. Here, I want to make the line a little bit smaller. Let's go H3 connected to a nitrogen, which is connected to CH3, and that's connected to a hydrogen, and this has a lone pair of electrons on it. Then I've got water, which is a bent molecule, and I got my lone pair of electrons here, and lone pair of electrons there, and this hydrogen is slightly electropositive, or is electropositive, because the electrons in this covalent bond are kind of hogged away from it because oxygen is more electronegative than the hydrogen. This lone pair of electrons is attracted to that hydrogen. And that hydrogen ends up jumping onto the surface, or, we can think of it that way. That hydrogen jumps onto that lone pair of electrons. And that's how we go from CH3 to, here I got my two CH3s, and my H, original H. And now we have an extra H on it over here. And that's because this lone pair of electrons was attracted to that electropositive hydrogen. And when that electropositive hydrogen is removed, I end up with that electropositive hydrogen is here on this molecule. And that's where we get this. And then I end up with the OH, and I end up with a negatively charged ion, which is this. You need to know that. Okay. And now we got to make an ice chart. Okay, so we're going to go I, C, E. This is initially 0.5 molar. This is in large excess. Let me squiggle it out. Initially, this concentration is 0. Initially, from pure water, this concentration is 1.0 times 10 to the minus 7 molarity, assuming this reaction happens at 25 degrees Celsius. For our purposes, for this calculation, that is so close to 0 that we're going to say, you know what, that's close enough to 0 that we're going to treat it like it is 0. That means the reaction is going to have to initially go this direction. That means this will be minus X plus X and plus X. And then equilibrium, we will have 0.5 minus X. 0 plus X is X. 0 plus X is X. The equilibrium constant for this will be CH3, 2 of those, and H with a 2, plus charge, concentration of that at equilibrium. I'll put a little E here to remind us at equilibrium. Hydroxide ion concentration at equilibrium divided by CH3 and H, whoops, that needs to be parentheses 2, square brackets, at equilibrium. Put a little E there to remind me. And turn that into math, that's going to be x squared over 0.5 minus x. And now I need some kind of number to go here to calculate something. What kind of k is this? Well, this is acting like a base. It is receiving an H. So this is acting like a Bronsted-Lowry base. This is acting like a Bronsted-Lowry acid. So this right here is acting like a base. So this is Kb for base. And also the fact that I have a hydroxide in there is kind of an indicator that's a base. So I need to go and look up that number. I went ahead and looked up that number, and you have that table. You have those numbers in the handout that I gave you guys, the appendices. But you can look this up online. Google Kb for dimethylamine solution. The numbers will vary a little bit because remember, it's an experimentally determined number. And this is going to be 5.9 times 10 to the minus 4. Well, that gives me a quadratic equation, but 0.5 divided by 5.9 times 10 to the minus 4. I calculated that. That happens to be equal to 847. That's greater than my criteria of 400, so I can use the x is small approximation. So I end up with x squared over 0.5 is equal to 5.9 times 10 to the minus 4 if I use the x is small approximation. When I'm done solving, multiply both sides by 0.5, take the square root, I will get the hydroxide ion concentration is equal to x. How do I know? A hydroxide ion concentration at equilibrium is equal to x. And that will be equal to 0.0172 molarity, or 0.017 molarity. But I asked for the pH, not X. So I need to clear this out, make some space here. So I'm going to erase some stuff. I think I'll erase this. So I can calculate the pOH. pOH will be minus log the hydroxide ion concentration. That'll be minus the log, log log, 0.017. That's two significant figures, so that means I write my pH number to 2 decimal places. And I get my pOH number. 1.77 is my pOH. And then I want my pH value. pH will be equal to 14 minus my pOH, 1.77. And when I do that, I get 12.24. So for this problem, I end up with a solution of, I'll put it over here, right? I end up with the pH of this solution when I'm done is equal to 12.24. What did I say before? I don't remember what I said before, but it's 12.24. And that's how you do those. You have to remember that what you're calculating here is KB, and what you're getting for X is hydroxide. If you take the minus log of this and you tell me the pH is 1.77, that's a big mistake because this is a basic solution. And if you told me the pH is 1.77, that's a highly acidic solution, but this is acting like a base. So it means you flubbed somewhere. Okay, anyway, that's how you solve these problems. I hope that helps.